Hello and welcome to this second video on fluid flow in pipes, in which we'll be looking at the Bernoulli equation and how to apply it. So just to quickly recap what the objectives of this section on fluid flow are, we have already covered the differences between turbulent flow and laminar flow in the previous video, as well as how to determine the flow regime present by simple calculations. So in this video we're going to be looking at how to calculate the head losses in a pipework system, how to calculate frictional losses in a pipework system, how to specify pump requirements for a system, and hopefully we'll be giving you some insights into the practical process considerations off the back of this as well. All of this will feed into the tutorials that we're going to be doing for the next couple of weeks. So just to recap what we've been doing in this section so far, we've already looked in the last video and in the tutorials at predicting flow characteristics in pipework, including laminar, transitional and turbulent flow, the Reynolds number and friction in fluid flows. So in this video today we'll be looking at how to calculate head in a pipework system. Before we do that, we'll have a quick recap of conservation of mass and energy, which underpins the Bernoulli equation. Then we'll look at how the Bernoulli equation is derived and what it signifies, and then we'll look at how to use it to calculate pipe friction and how to calculate frictional losses as well. So before we actually have a look at how the Bernoulli equation is used to tackle design problems of fluid flow, we first need to have a look at the fundamental concepts of conservation of mass and energy, which you will hopefully remember a little bit about from BEng 101P. These underpin the Bernoulli equation, and this equation allows us to calculate the total resistance to flow, also known as the total dynamic head, which is generated in a given pipework system. So the questions that we'll be answering initially are: what do we mean by head? Why is it useful to calculate heads in a pipework system? And how we go about determining pump requirements for a system. So starting with the conservation of mass. The conservation of mass is a fundamental concept of physics, along with the conservation of momentum and the conservation of energy. And in simple terms, it states that the amount of mass in a system remains constant, so mass is neither created nor destroyed. So for example, if you squeeze a toothpaste tube, whilst the toothpaste might be squeezed out of the tube, the total mass of the toothpaste both before and after you squeeze it will remain the same. So if we consider a typical control system with respect to conservation of mass, which is illustrated diagrammatically there, we have an inlet, a pipe inlet and a pipe outlet with a turbine drawing fluid up and pumping it out through the outlet. To express the conservation of mass mathematically, we need to consider a few quantities of the system, a few properties of the system. Those are the area normal to the velocity, so the cross-sectional area of the pipe, the fluid velocity in meters per second, h, the height above some datum or reference point, p, the pressure on the fluid in newtons per meter squared, and rho, the density in kilograms per meter cubed. And we need to think about these at two different points, so the inlet and the outlet of the system. So as a result of conservation of mass, we can say that any mass going into the system must also come out of the system. There's no retention, there's no destruction of the mass within the system. So if you apply the conservation of mass to flow in pipes, then the mass flow rate in, so the rate of movement of mass into the pipe network, must be equal to the mass flow rate that comes out of the pipe network. So any mass that you move in will displace mass from within the system, and that will come out at the same rate. Now you can calculate the volumetric flow rate in a pipe system by using Q is equal to UA, where A is the cross-sectional area of the pipe. Therefore, the mass flow rate is given by m dot is equal to rho, the density of the fluid, multiplied by U, multiplied by A. Note that m dot denotes mass flow rate and should not be confused with m, which is just static mass. So in our flow system, in our pipe system, the mass flow rate at two different points across the system should be equal. So ρ1 multiplied by u1 multiplied by a1 should be equal to ρ2 multiplied by u2 multiplied by a2. So the conservation of energy is very similar to the conservation of mass, and in simple terms it means that the amount of energy in a system remains constant. And again, energy can neither be created or destroyed. Energy can be converted from one form to another. So for example, potential energy can be converted to kinetic energy. So if you drop something from a height, before you drop it, it has potential energy, and then after you let go of it, that potential energy is converted to kinetic energy. But the total energy within a system remains fixed. So it can transform from one form to another, but the energy overall remains fixed. The unit of energy, as you'll hopefully remember, is a joule, denoted by a capital J, and its SI base units are kilograms per meter cubed per second squared. The mathematical equations for calculating the different forms of energies that we're interested in are given in the slide there. So you have potential energy, EPE, which is equal to the mass multiplied by the acceleration due to gravity g multiplied by height, and that is the energy due to the position above the ground, essentially. You also have kinetic energy, EKE, which is equal to a half mass multiplied by velocity squared, and that's the energy due to the movement of the fluid. So if we think about an energy balance, which you may not have encountered before, known as pressure energy, the conservation of energy tells us that the total amount of energy at W there is equal to should be the same mass. So the sum of the potential energy divided by the dense pressure energy should be energy due to pressure, regardless of what point fluid that we look at has. So if we define two arbitrary points, point 1 and point 2, then the potential energy, the kinetic energy, and the pressure energy at point 1 will be equal to the potential energy, the kinetic energy, and the pressure energy at point 2. Now we can substitute the equations that we showed on the previous slide into that equation, and that gives us what is approaching the form of the Bernoulli equation there. So the mass multiplied by gravity multiplied by height at point 1, plus the mass multiplied by velocity squared at point 1 over 2, plus the pressure at point 1 multiplied by the mass divided by the density, is all equal to the potential kinetic and pressure energies at point 2. Note that as we are dealing with incompressible fluids generally, we can say that the density at point 1 and 2 are the same, so density 1 is equal to density 2, and the mass at the 2 points is also the same. But as we are considering flow of fluid, it's more convenient to think of the mass flow rate, m dot, instead of mass, m. So the conservation of energy also means that if we are flowing fluid into a system, the rate of energy input that's coming in with that fluid is going to be equal to the rate of energy output that's going out with the fluid. So we can substitute m dot in for all of those m values in the equation above, and that gives us the equation at the bottom there. So if we take the equation from the previous slide and divide the whole thing by m dot g, so the mass flow rate multiplied by the acceleration due to gravity, what we end up with is the Bernoulli equation. So h1 plus u1 squared over 2g plus p1 over rho g is equal to h2 plus u2 squared over 2g plus p2 over rho g. So h there is the potential head, so the head due to potential energy. u1 squared over 2g is the kinetic or velocity head, so the head generated by the energy due to movement of the fluid, and p1 over rho g is the pressure head, so the head due to pressure applied to the fluid. Each term of the equation represents the energy per unit weight of fluid. So it's energy divided by m dot g, where m dot g is the unit weight of the fluid, or in fact the rate of weight change through the system. And each term also has the dimensions of length, so it's all defined in meters. So you should note that because we are dealing with mass flow, the Bernoulli equation only applies when there is actually flow of fluid occurring. So we've been using this term head a lot, but we haven't actually defined what it means. So head is a general term for pressure, either in a system as resistance to flow, or as a pump's capability to overcome the resistance in a system. So what head refers to essentially is the height of a column of water that a pump can raise. So if you think about a pump connected to a vertical pipe, the amount of power it has can be defined as the amount of fluid that it can raise to a certain height within that pipe, within that vertical pipe. So the higher the pump can raise the fluid, the more power it has. and the more energy it is giving the fluid. Head is always given in units of length, so in meters, so that pump charts can be universal. So it's basically a trick for making engineers' lives easier. And once you have defined the values of the potential, kinetic and pressure head for a system, you can confidently figure out what pump power you'll require. So let's have a look at what these different terms mean. The potential or static head is the difference in elevation between two reference points, so described as position 1 and position 2. Typically we'll be dealing with fluid being pumped out of a vessel. So position 1 in that case would be the liquid surface level of the vessel, and position 2 would be the end of the pipe, basically, so the point at which the liquid would enter the atmosphere, the point at which it would enter another pipe if it's injected into another line which we're not considering, or the surface level of the receiving vessel if the liquid is entering the vessel below the liquid surface. Note that we are only interested in the final difference in elevation, so the final elevation achieved. So there's no consideration made for the maximum height the piping may reach. It might go over the Alps, for example, but as long as the inlet and the outlet are at ground level, it's only that difference between the inlet and outlet that we are interested in. The kinetic or velocity head refers to the energy necessary to overcome the inertia of the fluid. So it's the kinetic energy that's generated by virtue of the fluid motion. The relative contribution of the kinetic head term is going to depend fundamentally on the liquid velocity, since it's proportional to the square of the liquid velocity. Hence, a double in velocity, for example, due to a reduction in pipe diameter, will increase the kinetic energy fourfold. If you're looking at a pipe system where the diameter is the same at position 1 and position 2, then by conservation of momentum, the velocity of the fluid at these 2 points should be the same, and so the terms on either side of the equation will cancel each other out. If alternatively you're looking at a system where the pipe diameter at position 1 is much greater than the diameter at position 2, then you may be able to cancel out the velocity head at position 1, because relatively speaking the velocity will be much smaller at position 1 than it will be at position 2. And so you may be able to neglect the U1 kinetic head term. We'll cover some examples of this in the tutorials that we're doing next week. The pressure head term represents any differences in pressure between position 1 and position 2. So position 1 is the pressure in the source vessel or source pipe, which might be negative if there's a vacuum operating the vessel, 0 if the tank or the pipe is open to the atmosphere, or positive if you have a pressurized vessel, for example if you're pressurizing the fluid in order to pump it out of the vessel. Position 2 is the pressure at the point of discharge out of the pipe or into another tank, and similarly maybe negative, 0 or positive. So there are some limitations in the basic form of the Bernoulli equation that we've been looking at so far. The equation assumes that there is steady flow, which is a common assumption that's applicable to many flows, so that's okay for us. It also assumes that there is incompressible flow. Again, that's a fairly common assumption. It's valid only for a flow along a single streamline, but we don't typically look at more than one streamline at a time. And it also assumes that there's no transfers of heat, which is fine as long as we are not dealing with a heat exchanger in the system. However, the two assumptions that are a bit of a problem for us are that there is no shaft work, so there's no pump or turbines on the streamline that are adding energy to the system, and also that there is frictionless flow, and that's particularly very restrictive because solid walls always introduce friction effects on flow. So those last two assumptions are not particularly reasonable, and the equation has to be modified in order to take account of them. So we can make two modifications to the Bernoulli equation to take account of the friction losses and the work done on the system. So the first of these is the friction losses resulting in head loss, and this involves the addition of a head loss by friction term, delta HF, as shown below. The second term is the work done on friction losses, i.e. by a pump. So we're adding energy to a system using a pump or turbine. And this involves the addition of the pump work term, delta capital P, over m dot g. Note that capital P indicates power, where small case p indicates pressure, so make sure not to get those two confused. So we add those to either side of our modified Bernoulli equation, with the delta P over the pump work term going on the left hand side and the friction head term going on the right hand side. So these two terms are in opposition to one another. Friction losses cause head loss, whilst the work creates additional head. And here delta P is defined as the rate of doing work by the pump, so it's the power input from the pump, and that has units of watts or joules per second, and delta HF has units of meters, as with all of the other terms. The significance of the modified Bernoulli equation is that it tells us that the difference in height, velocity squared and pressure all make a difference to the amount of head loss in a system. And these differences, along with the friction existing between 2 points on a pipe, determine the amount of energy that we need to add to the system, or add to the fluid in fact, by a pump in order to overcome the pressure head losses. Note that in deriving the Bernoulli equation we assume the fluid velocity is constant across the pipe diameter. This is approximately true for turbulent flow. As you'll remember from the flow profiles that we discussed in the last video, most of the flow is occurring at the same velocity, but this is not true for laminar flow, where you have a range of different velocities across the width of the pipe. So for laminar flow we have to add a correction term to the Bernoulli equation to make it valid. However, we are only going to be considering turbulent flow systems in this work. The friction head term delta HF is actually derived from the force balance that we used to derive the Harden-Presel equation in the last video. It's not particularly important that you know how to derive the equation for the friction head. You do need to understand how to apply it, but if you are interested in how it's derived, I'll be doing a separate video showing briefly how we can derive it from the force balance around a cylinder of fluid in a pipe. So delta HF is equal to the fanning friction factor, F, multiplied by 4, multiplied by the pipe length over the pipe diameter, multiplied by the velocity in the pipe squared over 2g. And this formula is sometimes called the Fanning's friction formula, where F, the fanning friction factor, is equal to the shear stress at the wall divided by a half density multiplied by the acceleration due to gravity multiplied by velocity squared. The fanning friction factor is actually a dimensionless group, which is something that you can check for yourself if you insert the units into that equation there. For turbulent flow, the friction factor is affected by the surface roughness of a given pipe. So the rougher the surface, the more friction will be generated. But in laminar flow, it's completely independent of surface roughness, and in fact is only affected by the Reynolds number in the pipe. So at Reynolds numbers of less than 2000, the friction factor is independent of roughness. At Reynolds numbers between 2000 and 2500, the friction factor increases rapidly and the relationship becomes non-linear. And then at Reynolds numbers over 2500, the friction factor becomes dependent on both roughness and Reynolds number. So at low Reynolds numbers, i.e. in laminar flow, so typically at Reynolds numbers below 2100, the fanning friction factor can be calculated from the equation F equals 16 over the Reynolds number. So it's dependent solely on the Reynolds number, it's independent of roughness. At high Reynolds numbers, so at Reynolds numbers over 2100, the friction factor is dependent on turbulent flow, and it becomes a function of both the Reynolds number and this term E over D, which is the relative roughness of the inside surface of the pipe. So in this term E over D, E is the absolute roughness of the pipe, usually defined in millimeters. D is the diameter of the pipe, and E over D is the relative roughness of the two. This value E, the absolute roughness of pipe walls, can be defined as the difference in height from the minimum surface of a pipe wall to the maximum surface of the pipe wall. So if you look at a pipe with the naked eye, typically you'll see quite a smooth surface, but if you were to look at it under a microscope, you would see quite a lot of variation in the actual surface of the wall. So for rougher pipes, or pipes made out of coarser materials, the difference in the height between the minimum surface of the wall and the maximum surface of the wall is going to be bigger than in pipes made out of finer materials with smoother walls, where the difference between the minimum and maximum surfaces is going to be smaller. And this difference between the minimum and the maximum point of a wall, when you're looking at it on a microscopic scale, is known as the absolute roughness, and is defined in millimeters. So some values of absolute roughness in millimeters are given in the table on the slide there. Notice that for drawn tubing, which is quite a smooth material, the E value, the absolute roughness, is 0.0016 millimeters, whereas compared with cast iron, which is quite a rough material, the absolute roughness is 0.26 millimeters. So there's quite a large difference there, and that difference is going to make a lot of difference to the friction that's imposed on the fluid flowing through those pipes. Now, the relationships between the Reynolds number, the relative roughness, and the friction factor are shown on a Moody chart. And there is also an equation that relates the friction factor to the Reynolds number and relative roughness, but it's incredibly complicated and quite difficult to remember for an exam. So a Moody chart is typically the best way to find a friction factor once you've determined the Reynolds number and the ratio of E over D. A quick note on calculating E over D: because the absolute roughness values are given in millimeters and the diameter of pipes are typically given in centimeters or meters, you need to make sure that the units in the relative roughness are the same on the top and the bottom. So you need to convert from millimeters to meters in order to make sure that you get the right value of relative roughness. The Moody chart, as I said, relates the Reynolds number and relative roughness to the friction factor inside a pipe. So it's a log-log plot, effectively, of Reynolds number and friction factor, with several different lines representing different values of relative roughness, all on the same plot. So to read off a value of friction factor for a given E over D and Reynolds number, what you first need to do is find the line that corresponds to the value of E over D that you've calculated, follow that up to the point at which it meets the Reynolds number that you've calculated, and then read off the corresponding value of friction factor, F. So for example, if our E over D is 0.0004, we follow the line for 0.004 over to the Reynolds number of 10 to the 5 there, and from there we read off that the value of friction factor, F, is 0.0049. And we'll be doing some more examples of finding friction factor using Moody charts in the tutorials, as it takes a little bit of practice to get right. Once we have our friction factor, we can calculate the head loss that's going to occur due to friction imposed by the surface of the walls. But so far we've only been, that only accounts for the frictional losses due to the walls of straight pipes. And the friction head term is also used for head losses due to friction in bends and fittings, such as valves, pipes, and pipe bends. So how do we calculate these? Well, each type of bend and fitting in a pipework system has a resistance that can be expressed in one of two ways. Either as a length equivalent, LE, which relates the resistance in the fitting to an additional length of pipe, which can be increased or decreased depending on the kind of fitting and the amount of resistance that it causes, or as a number of velocity heads denoted by the letter K, which is another value which is multiplied by the velocity head in the delta HF term in order to add the additional resistance that extra fittings can cause. So there are two different equations that are used to calculate delta HF, depending on whether you're using the velocity heads method or the length equivalence method to take account of your bends and fittings. If you're using the velocity heads method, then the friction losses are described in terms of velocity heads and are calculated using the equation on the right there. Delta HF is equal to K multiplied by U squared over 2G. Remember that U squared over 2G is the velocity head, so K, a K for value for a particular fitting is expressing the resistance of that fitting in terms of velocity heads. For length equivalence, they are calculated using the standard equation, delta H equals F4L over D multiplied by U squared over 2G. And you simply add the length equivalents to the total length of pipework. So length equivalents are usually given in terms of equivalent diameters. So for example, for a bend, you might have a length equivalent of 22 dp, where the dp is the diameter of the pipe. So if your pipe diameter is 0.1 meters, then 22 dp would give you a length equivalent of 2.2 meters for that fitting. And what you do with those is you sum them all up, add them to the total length of pipe, and then put it into the equation for delta HF. So when calculating the frictional losses or the total frictional losses for a system, you need to pick whether you want to use velocity heads or length equivalents to characterize the friction loss due to bends and fittings in your system. Whichever you choose, you need to sum up your total either velocity heads or equivalent pipe lengths before putting it into the relevant equation for delta HF. So you need to sum up the velocity heads for all components in the system, as well as the length if you're using K values for your fittings, or you need to sum up the length of pipe and the equivalent length for your fittings if you're using equivalent lengths. So the friction losses caused by different fittings are already very well characterized and widely available as either K factors or length equivalents. For inlets and outlets, you will have a K factor of either 1 or 0.5 respectively, and that's the additional resistance caused by the fluid either entering or exiting the pipe. You'll also have extra resistance as a result of bends and joins, and the friction loss factors depend on the type of bend that you have. So some bends will cause more resistance to flow than others. Those are summarized in the table on the slide there, and I'll also be putting them on Moodle as a separate slide for your reference. Valves will also cause a certain amount of friction loss, and the amount of friction loss that they cause will be dependent on how much the valve is open. So, for example, the globe valve that is fully open will give you a K factor of 7.5, whereas a gate valve that is fully open will give you a K factor of 0.15. But if you begin to close the gate valve, the K factor will slowly increase. So the resistance that it's causing to flow, the friction that it's causing, is increasing. So closing a valve restricts the amount of fluid flow that's able to pass through the valve opening. And actually having the valve fully closed gives you pretty much an infinite resistance to flow, so no flow will occur at all. As you start to open the valve though, the resistance to flow will decrease, and it will continue decreasing as long as you keep opening the valve until it is fully open, where the resistance to flow will be minimum, and so the K value or the length equivalent of the valve will also be at its minimum. So the general steps that you need to follow in order to solve a Bernoulli problem are summarized here. To start with, you need to apply the Bernoulli equation to the system, and you need to identify points 1 and 2. So those are your two reference points that you're interested in for that system. That might be the surface of liquid level in a tank for point 1 and the outlet of a pipe heading into another tank for point 2. The next thing you do is identify where you might be able to simplify the Bernoulli equation. So for example, if both tanks are open to the atmosphere, you can assume that the pressure in both tanks will be atmospheric, and so those terms will cancel out. The next step is to calculate delta HF, so your friction losses. So for fittings with K values, what you need to do is sum all of the K values for the fittings. For fittings with equivalent lengths, you need to sum all of the lengths of pipe and the equivalent lengths for the fittings, and then calculate the velocity, calculate the Reynolds number, calculate E over D, find F from the Moody chart, and then if you're using K values, calculate K is equal to 4 LE over D, so 4 times the length of the pipe over the diameter of the pipe, and then sum those up and put them into your equation for delta HF. Then all you need to do is substitute the values into your modified Bernoulli equation and solve for whatever value you've been asked to find. For example, usually we ask you to find the pump power required to overcome the head losses in a particular system, so delta capital P. That might all seem a little bit complicated now, but we're going to be doing plenty of examples in the coming weeks in some tutorial sessions, and so with some more practice you should be able to develop an understanding of how to solve these Bernoulli equation problems and how to specify pumps for a specific system. So that's it for this video. If you'd like to find out how we derive the fanning friction formula from the Hagen-Poiseuille equation, I will be doing a separate video for that, which will be available on Moodle soon. Otherwise, do have a look through the K and length equivalent values for different fittings that I'll make available on the site, and I will see you in the tutorial sessions next week.